What's up, guys? Let's talk about server-sent events. I've seen a lot of things on server-sent events, and it seems like most people don't really understand how they work. So I want to try to break it down for you. Server-sent events aren't any special protocol. It's just HTTP. That's it. It's just a response type in HTTP. I think one thing that confuses people is a conflation of connections and responses. So let's quickly break that down. Connections are simply TCP sockets managed by the browser. The browser manages these in connection pools. It's different for different versions of HTTP, and requests and responses execute over these connections. So way back when HTTP first came out, it worked like this. The server would just send data. There was no length indicator on the data in the response. The server just closes the TCP connection to signal that it's done with the response. The client had to wait for the connection socket to close to know the response was complete. This could be confusing because we didn't know if the response finished or if there was an error. And the connection couldn't be reused. You had to open a new TCP socket for another request. So then in HTTP 1.0, the content length header was added. The server would send data with the length indicator of the data. The server still closed the TCP connection after sending the data. But the client did not have to wait for the connection socket to close to know the response was complete. And we definitely know the response finished or if it errored. But you still had to open a new TCP connection for the next request. So it looks something like this. A three-way handshake took place between the client and server, and it established the TCP connection. And when the connection was established, a request could be made. So you'd make a request, and then you'd get a response. And once the client received the response, the connection would close. And that was it. So let's see a quick demo of this. I created a situation mocking HTTP 1.0. I'm going to make some requests, and I close them immediately after. We can see I have the connection close header here that closes the connection after the request is done. And I'm going to analyze the waterfall for this request. You can see there's a good amount of time spent on initial connection. And if we click on explanation, we can figure out what this is. And it says here that the initial connection is the browser establishing a connection, including TCP handshake or retries. So that timing we saw is it establishing the TCP socket connection. And we're not doing any security on this connection, so it's not negotiating anything. So let's see this with multiple requests. I'm going to make requests, and it's going to close between requests. And you'll see it's a little slow. You can also see that each connection ID will be different. So people quickly realize that this is pretty wasteful. We can reuse a socket if we want to for another request. So then an unofficial extension was made. They added the keep alive header. The client must explicitly request it, and the server must agree with it. The content length header was used to separate responses. It was needed to know when the response was done. Then the connection could be reused. So with HTTP 1.1, this became default. And now you get to your standard request response. The response is sent and the connection can be reused. This reduces that TCP handshake overhead we saw. The server can close the connection anytime after a response completes. And this is based on things like timeouts or max requests. And so it looks something like this. The client wants to make a request and it does the same TCP three-way handshake, and then it establishes the connection. And then you send your request, and then you get the response. And then when that response completes, the connection stays open for the next request. So let's do another little quick demo. This time after each request, the connection will stay open. So I'm just going to keep clicking and making requests, and you'll see them come in, and you can see they're coming in a lot faster than they were before. And if we analyze this further, we can see the connection ID stays the same. And you can also see the TCP handshake only happened on the first request. We have a keep alive of 5, which means after 5 seconds, it will drop the connection. So now the question arises, what if we don't know the size of our data that we're sending? What if it's dynamic and we're sending a bunch of different data? And that's where chunked encoding comes in. Chunked encoding allows you to send dynamic sized data. And the way it does it is it demarcates each message in the response. Each chunk has a size in hex, then a carriage return, then data, then another carriage return. So it's giving you the size of each message. but it's not saying the response is done. A 0 chunk indicates the end of the response. And after the terminating chunk, the connection can be reused or it can be closed. There's really no point in doing that though. This allows the response to start sending messages immediately, so the response isn't buffered. You don't need to know the length of the entire response. And again, the connection knows the response is complete when it sees the 0 chunk. And this is below the application layer, so you don't see this. So we don't need to send the response all at once. We can send it in parts, and this allows us to do some cool stuff. You can stream your response. Using chunked encoding, we can end our response whenever we want. The client reads chunks as they arrive. This connection and response just stays open. Some intermediate proxies might buffer, but you have headers that can control that. But the big thing is, if there is a problem, there's no automatic reconnection, unlike server-sent events. So I have another little demo here that'll show this off. When I click the button, we're going to make a request, and using chunked encoding, we'll get our response. It's going to come in pieces. And you can see here I appended each chunk. And this is what the finished response ends up looking like. And you can see here, it's just basic headers. And again, the response will end, but the connection will stay open for reuse. Here I click it twice and you'll see the TCP handshake for the first one, and the second one will use the same connection ID. Now the moment you've all been waiting for, server-sent events. So server-sent events traditionally use the event source API. You use this to start requests. You can add a retry field, so if it loses connection, it'll try to reconnect. It keeps track of the last event ID from the server so it can resume where it left off. And it uses built-in event listeners, but you can write custom ones that go with custom events you write. So the way it works is pretty simple. It's just a content type header. Instead of text plain, it's text/event stream. Messages are delimited by double new lines, so you send data with your content and then double new lines to finish that specific message. You can add custom event types, IDs per event, a retry interval for the event source API, and even comments. It's really not any different from a request response with chunked encoding. You just have a special message format. And you can send 0 to as many messages as you want. So you can send 1, 5, or just keep it open and continue sending. You choose when to end the response. And the connection management with the browser is the same as the previous examples. So the browser's event source API again handles parsing of these messages, as well as reconnection if a connection drops. Again, it can resume on the last event ID. And again, it's using chunked encoding underneath. But this is only for HTTP 1.1. It gets even better for HTTP 2 and beyond. HTTP 2 has its own default data framing. So there's no complex state management like WebSockets. There's no special protocol like WebSockets. You don't need a special server. It can be compressed, and there's a lot of interesting things there that we'll save for another video. It works entirely within the HTTP protocol. It operates through the standard ports, passes through proxies and firewalls without special configuration. Again, supports automatic reconnection and tracking. The connections are managed by the browser again for request response or SSE. It's just a response type with a simple defined format, and it lives as long as you want it to. That's it. And once again, it's just HTTP, nothing special. Let's do another demo, and in this one, I'm going to show just sending a single message with SSE. So I start the connection, send a request, and I get a response. I have quite a few things running at the same time right now. That long handshake isn't representative of SSE. So you can see the response being appended here. We can see the content type response headers here. And we can click event stream and actually look at the event that came through. See, it's just text. And if I rapidly click and make multiple requests, you'll see it's no different than any other request. I'm simply choosing to send one message. You'll also notice it's reusing the same TCP connection. And here's an example with multiple events in one response. I make the request and the response just streams events through, so I just get multiple messages in one response. Under event stream, I can see the messages that came through. I can watch them come through live if I want to. And see, the response didn't have to live indefinitely. I got to choose how many messages I sent in one response. And there's nothing special going on here. The same headers, just content type text/event stream. And if I run this twice, you'll see it'll reuse the same connection. Again, connections and responses are two different things. I've got one more demo here. And for this one, we're going to show how SSE can reconnect. We're going to use the last event ID and the retry field. So on the server side, when I landed on this page, I started generating events. When I click Start Connection, I'm going to hit the SSE endpoint and start consuming these events. And we're just going to stream this data. So you can see the data start flowing in. And I'm going to mimic an error on the server. We're going to cause a disconnection. And I clicked it, and it looks like the last event was 30. So when we resume, we should start on 31 and receive any other events that have happened since. And bingo, we got 31 and 32. So again, it's just HTTP, nothing special. The special part is Datastar. The event source API has some big limitations. You can only use GET requests, so your URLs can get extremely long. It's also significantly less configurable. But because it's just HTTP, it's extremely extendable. Some people at Microsoft made a Microsoft Fetch event source library. This lets you use the Fetch API to do this instead of the event source API. Now you can do post, put, patch, delete. Remember, SSE is just a response format in HTTP. Datastar actually rolls its own extension and has no dependencies for this. This makes Datastar use it in an extremely powerful way, which we'll go into in the future. Again, SSE responses live as long as you want it to. It's just a response type. And Datastar has SDKs that do all the response formatting for you. We'll get into the Datastar response formatting in another video. Now there are some browser-based caveats for this, but it's mostly just for HTTP 1.1. Since HTTP 1.1 is one request per connection, you can end up consuming all your slots for these connections. Browsers typically limit to 6 connections at a time. When all 6 are taken up, a request will be queued, waiting for a connection to open up. Long-standing connections will take up 1 slot. The trick is to just manage your connections. If you're sending a few events, then just send a few events. And if you need the connection to be long-lived, just dedicate 1 connection. And you can use some sort of event bus situation on the back end and reuse that same response. But the best thing you can do is just use HTTP 2 or 3. They don't do chunked encoding. They multiplex requests and responses over the same connection. So you can have 1 connection that handles multiple requests and responses. This gets rid of almost all the annoying things we had to go over in this video. Connection management becomes almost irrelevant, and you just don't have to worry about it. And now I'll show you head-of-line blocking. So this server is HTTP 1.1. I'm going to make 30 parallel requests, and you'll see them executed in batches of 6. You'll notice all first 6 of them will have the TCP handshake for a new connection per request, and then each of those connections will be reused. And this is quite slow. And if we filter on connection ID, you'll see it's the same 6 connections. Now let's do the same experiment, but this time with an HTTP 2 server. And you'll see all the requests multiplexed over the same connection. And it's way faster. Bam! So remember guys, it's just HTTP. Server sent events is just a response that lives as long as you want, sends 0 to however many messages you want, and you're just using a specific format. Data, then your content, separated by 2 new lines. And that's all there really is to it.